My name is Daniel Soto. I teach in the Department of Geography, Environment, and Planning at Sonoma State University. And I'm really grateful for the invitation to talk to folks today. I want to talk a little bit about sort of my relationship with science and kind of how I decided to go on the path that I'm on right now. And then we're going to talk a little bit about the things that we get and enjoy from energy and the kinds of impacts they make on the environment and how we might continue to do the things we like to do, like drink cool beverages and take warm showers while having a less of an impact on the environment. So let's see, I'm going to share my screen. I've got some slides prepared. So here we go. So first I want to talk about just sort of my relationship with science. People get into science for a lot of different reasons. My interest in science is mostly about making things and learning about the world. So the big question that a lot of people on our planet are dealing with is how do we keep people happy and healthy while protecting the environment? So this is a really big question. We know from the evidence that climate change and global warming are causing increasing problems, and yet we want to maintain the life that we have. We want to still be able to travel freely and eat delicious foods and have cozy homes. So all of that actually has to do with energy. And so one of the things that interests me about science is that I view it as giving us tools in order to improve people's lives. So science gives us a bunch of rules about how the world works. And if we think about those rules, we can use them to predict the impacts of our actions and think about how to make things better for more people. So if you are interested in science, there are plenty of really interesting career possibilities for people who develop scientific expertise and ability and knowledge. And I think the two biggest things that I would recommend to anybody wanting to pursue science or engineering or related fields is develop your sense of curiosity and wonder and really think about just learn to ask the question why and how, and get really engaged in that question. That's one of the things that I've always loved is figuring out how things worked and sort of why things were the way we were and how fairly simple rules of science could make predictions. The other good thing is that all science work and engineering work and making things requires difficulties and setbacks. So perseverance, the ability to have a problem and then get clever about trying to work around a solution is a really good thing to be able to do. So in my education, I liked science as a young child, I guess sort of kindergarten. I liked burning things and seeing what happened. I liked lots of stuff. I liked electronics and blinking lights. I found all those things fascinating. When I got into high school, I remember I was still pursuing science, but I remember I had a hard time with the trigonometry class. And I was like, well, I don't know, maybe this trigonometry stuff isn't for me. But later I found with a little bit of practice that trigonometry was just fine. I can use it quite easily today. I could use it easily then. So sometimes our fears don't know our strengths. And so sometimes it's easy to tell yourself a story about what you can and can't do that is probably not true. So the story I told myself about not being able to do trigonometry turned out to be not true at all. So you know, as you persevere, be sure that you're telling yourself good stories about what you want to do. So, and then I took time off in industry. I knew I wanted to teach, so I knew that I needed to get a PhD degree in order to teach at the college level. But I did have some setbacks there. When I was an undergrad, I didn't apply myself very well in college. And so my grades weren't that good in college. And grades are very important for getting into grad school. So the first graduate schools, when I applied, I wasn't able to get in. And so that was difficult because I couldn't change my grades. I didn't have a time machine. But I got resourceful, applied to some other universities, and I got to go not for a PhD, but for a master's to San Francisco State University. And I was accepted and placed on academic probation the first day. So that's another example of just sort of, you know, rolling with the punches. My very first day enrolled at grad school, I was on academic probation. So that's part of my story about coming through. And then whenever you're building stuff or wherever you're making things, things just go wrong all the time. And so it can be fun to deal with those things. You can try to ask yourself little questions. Well, what am I assuming? And why do I think it went wrong? And how do I think it, how do I keep it from going wrong next time? And you get to run little experiments and try to figure out how to make it work. So for me, I'm a teacher, but I use science a lot. I teach science. I think about science when I'm teaching. On a typical workday, I spend a lot of time in the classroom helping students learn. I spend a lot of time reviewing student work. I write emails. I have meetings and talk with other people. And then I also try to spend every day thinking up and learning about new ways to help students learn about energy and the environment. I'm really interested. There are people that do research on education, and they are learning about the ways that students learn best, how they learn science best, what makes students happiest in the classroom. And those are things that I try to pay a lot of attention to. So that's a little bit about me, kind of me in science. Now my degrees are in electrical engineering for undergraduate college, and then I did physics and applied physics for master's and my PhD. And I'm interested in how sort of physics and all of that can help us with our challenges around climate change and global warming. So as far as what I want you to learn today that you might not have seen in a science class yet is about using energy wisely and the way that what energy is and how we turn it into stuff we want. So we kind of return to this big picture question that we started with, which was how do we keep people happy and healthy while protecting the environment? And so the things that I'm sort of interested in my teaching and when I do work is how do we get the thing we want? Again, a cozy home, a warm shower, a nice meal with less greenhouse gas emissions, more safety, more justice. These are all things that we think about a lot. And so I want to show you a couple of the concepts and rules in science that help us answer these questions and how they do that. So if I want to do something, if I want to drive to Katati, if I want to boil a cup of tea, how do I predict and measure how much energy it takes to do that? You know, how much energy is it going to take me this winter to drive a home, to heat my home or to drive a car? Later today, we're going to measure the energy to boil some water, and I'm going to show you a tiny little thing of water right here that I'm going to heat up for myself. So what are the rules and things that we know, that we need to know in order to do this? So before we talk about energy like we do in a physics class, I want to talk about what we call energy sources and energy services. So sources are often what we talk about when we talk about energy. We talk about solar energy, fossil fuels, wind power, coal, gas, oil. Those are sources of energy, but you and I don't really use those like directly. What we use are air conditioners, gas pedals, cars, stoves, hair dryers, light bulbs, computers. Those are the services that energy requires. So often it's really useful to think about what is it the thing that people really want, and then how can we do that that's different maybe than what we're doing now. So types of energy. There's a type of energy, if I throw a baseball, it's called kinetic energy. An easier word is just to say it's the energy of movement. If you've ever been hit by a baseball, it hurts a little bit, and that's because that energy is going from the baseball to your body. We have what we call chemical energy. If I take wood or gas or coal and I burn them, they turn from coal molecules into simpler molecules. And when they change from a molecule of gasoline into molecules of carbon dioxide and water, they release energy. We call this chemical energy. And this is one of the main ways that humans on our planet use energy. And that releases carbon dioxide. Radiation energy, if you've ever been around a campfire, that's the feeling you feel, radiation. Also, if you're using a toaster, that's radiation energy. Internal energy is a little complicated. I'm going to show you a picture in a minute, but that's what we experience as temperature. Just like a baseball has energy when it moves around, the little atoms inside our air or the molecules in our water are moving around. And if those are moving around faster, they have more energy. But we don't see that energy like when a baseball hits us, but that energy of all those billions and billions of little atoms moving around and molecules moving around is what we call temperature. And then electrical energy we all use all the time. Every time you charge your phone or your laptop, you're using electrical energy. So now, a quick word about internal energy. So because we're going to look at this more closely later. So the molecules in hot water are moving around faster than molecules in cold water. And that's called internal energy. And we measure that and experience it as what we call temperature. So keep that concept in mind. We're going to look at it in a little bit. And you can sort of visualize cold water, things aren't jiggling around a lot. Room temperature water, they're moving a little more. And in hot water, the molecules are moving around much more than they are in the cold water. So again, it's energy kind of like the baseball, but these baseballs are too small to be seen. They're little molecules of water. So one of the things that when we think about energy, what we're really concerned about as humans is this kind of stuff. Like we want to drive around in cars. We want to heat up our food. We want to get from point A to point B. And what's interesting is that how do we turn different kinds of energies into the things we want? So most of us are familiar with taking the chemical energy of gasoline, putting it into a car and turning that into motion energy or kinetic energy. Lots of us cook food every day, so we might take chemical energy and convert it into heat to cook our food, or we might have electrical energy converted into heat. So when we really want to think about new ways to get what we want, what we're really talking about is these energy transformations. So a good thing to think about is what kind of energy did we start with in order to get the thing that we wanted? So those conversions are what provide those services that we want to enjoy. A quick word about greenhouse gases again. Combustion, when we take chemical energy, all of our favorite forms of chemical energy, wood, coal, natural gas gasoline, oil, all of those things contain lots of carbon. And when we burn them, it turns into carbon dioxide. Carbon dioxide is our most important greenhouse gas right now. We know that that gas traps energy and heats our atmosphere. And we believe that that makes droughts more likely, hurricanes more likely, fires more likely. And so we want to think about different ways. So that means coming up with other energy conversions in order to get the things we want. So a couple of words about the units of energy. When you buy gasoline, you know that you usually buy it in gallons of gas. That's a unit of volume. Here we want to talk about energy. So in the metric system, which is my favorite system, I hope it will be yours too, we use a joule to talk about energy. So if you strike a match, it releases about 1,000 joules of heat energy. And then if you have a toaster, that's about 1,000 watts of power. Now, power is how fast you use up energy. So if you take the amount of energy you have and divide it by the amount of time that it took to release it or convert it, that's the amount of power. So a toaster uses about 1,000 joules a second. So a toaster is about like striking a match every second. That's about 1,000 watts of power, right? So if you strike a match every second, that's about 1,000 watts. 1,000 watts is also about what a hairdryer is. So those can help you think about, you know, how much energy and power stuff in your house uses. And your phone chargers are all about 5 watts. So those are actually really small amounts of power compared to your toaster. So now, how can we measure the amount of internal energy? We talked about a picture of the internal energy of water. So it takes about 4.2 joules to raise 1 gram of water, which fits in a little cube about that big, 1 degree Celsius. So if you know how much water you have, and you know how much hotter you want it to get, you can multiply by how much water you have, and then you can multiply by how much hotter you want it to be, and you'll know how much energy it'll take to do that. And this is important because the amount of energy it takes to do something is usually related to how much carbon dioxide gets released. So we're always trying to get the thing we want for the least amount of energy possible. But so if we, you'll see a formula later for this, but the main thing is if you know how much water you want to heat up and how much hotter you want it to get, you can multiply that by 1 more number, and then you've got how much energy went into it. You got to get the units right and all this stuff, but it's as simple as multiplying 3 numbers together. So let's see, I'm going to switch my camera. And show you, and I think I'm going to turn off my slides so that this looks nice and big. And let's see, so this is we got a couple things going on here. This is a hot plate. This is just like your stove at home if you have an electric stove. It's got a little knob, it's got a switch, and this is a little piece of electronics to do temperatures, and this is a temperature sensor. So you can see that little light go on. It's not very bright, but now we are heating up this water. And let's see, so that's what it looks like. This plate is going to get hot, and this is a little temperature sensor right here. So now I'm going to switch my screen again that you've seen that, and I'm going to show you a little graph. But first I need to plug something in. Give me just a sec. All right, and I'm going to share my screen. All right, so what you should be seeing right now is a little graph. There's four colored lines jumping around because my sensor has four temperatures. And then I'm going to stick one of them in the water, and the x-axis is time. You can see it's been running for about 40 seconds now, and the y-axis is temperature in Celsius. So room temperature is about 22 degrees, and then a really hot day outside is about 35 degrees, and boiling water is about 100 degrees Celsius. So this water's been heating up for a little while, and so we see that the black line is the one that must be in the water because it's getting warmer. And then as we look at that black line, we see that it's continuing to rise in temperature. So what that's telling us is that that formula I told you a little bit ago is kind of true. This plate is hot, and so energy from this hot plate is going into the internal energy of these water molecules. They are starting to move faster and faster. As that line, the black line, gets higher and higher, those little molecules are moving faster and faster. And if I look at this difference in temperature from, let's say, 26 degrees to 28 degrees, I could figure out, and I put about 100 grams of water in here. So if I multiply 2 degrees Celsius by 100 grams times 4, I know exactly how much energy I've put into the water. So we're going to use that same idea to figure out how powerful or how quickly is the energy on your stovetops being converted. And then, because this is just like many of your stovetops. Some of you have gas stoves. I have an electric stove. So this is almost identical to behavior to my electric stove. And so this is how we learn about how much energy. Often we're measuring temperatures and figuring out how much energy is going into buildings or when we make things in industry and manufacturing and all of those sorts of things. So let's see, let me go ahead and go back to my slides. So if we have ways of tracking these temperatures, we can often track the flow of energy. So measuring temperatures is the first part, is often one way that we figure out where energy is going, especially if we're wasting energy. If on a cold day, the outside of your house is warm, that is some kind of waste of energy. And people often need to be able to see that energy in order to make decisions. So hopefully those of you that are hanging out with us for the breakouts, you're going to look at some energy around your home and try to see energy and energy conversions. And then the last thing I want to say is if you want to learn more, there's a book called Drawdown that was published a couple years ago. I can provide these links. You're not going to be able to click on these links, but that book is an excellent description of 100 different ways that we can reduce greenhouse gas emissions. And you can think about a lot of those as different ways to convert energy. There's a really nice video interview with one of the authors, and then they've got a nice website with a lot of the solutions. And any of you are welcome to contact me with questions in the future at this email address, SOTOD for Daniel Soto at sonoma.edu. And that is my presentation for today. So I think we're going to go. I saw a hand raised. I think we might go to question and answer now.
Yeah. If everybody could just put your questions into the chat. Dr. Soto, I wanted to ask you a question first because you've been a really important mentor to me, and I wondered if you could tell us about one of your mentors.
Yeah, I have several. Let's see here. Let me get this camera back on me. Gosh, there's so many to choose from. Who do I want to choose? One of my earliest mentors was a scientist named Dr. Bill Banier. When I was an undergrad, let's just say that my potential wasn't obvious to everyone. And he saw my potential. He took a risk on me and let me work in his lab that he worked at. I showed some promise. That led to a job. And he was really important in teaching me science, but also teaching me how to sort of be a professional. Those were all important lessons. And then since then, other professors and educators of mine have gone on to be mentors to help me think about being better researchers, better teachers. And it's never too late to have mentors. I still sort of have people that I consider mentors for myself.
Thank you. Okay, so from Aaliyah, we have a question. Through your job, what improvements do you hope to see in the next 5 years?
Well, let's see. Well, I hope to see, so the things I'm interested in renewable energy, I think that electrification of transportation has a lot of potential to reduce carbon. I think there's a lot of more room for renewable energy right here in Sonoma County. So I'm hoping that Sonoma Clean Power and the way that we are having more and more Sonoma County citizens choosing where they get their energy is going to allow us to create more energy sources here in Sonoma County. And Sonoma Clean Power is also creating a storeroom or a storefront where they're showing energy efficient technologies so that not only can we get our energy sources from the places that we think are good, but our energy services we can get from things that we think are more important. So, are going to be just better ways to get those energy services.
All right, we have another question. What are some ways to lower the economic barriers to energy access in underdeveloped countries?
That's a good question. I am not, so this is, if you were interested in this, you can learn more about energy policy. I think what the main question is what gets to, is it easy or hard for people to get access to loans? If you look at the history of the United States, there are times when it's been easy for us to get loans for things, and there have been times when it was hard to get loans for things. And we want to be able to make loans safe and simple. Otherwise, we have problems like redlining, where we weren't giving people loans based on the color of their skin for houses, and problems we still see where a lot of people think that the loans we gave in the 2000s led to the economic crash of 2008. So I think one of the biggest things is not really the technology, but we have to make it easier for these countries that want these renewable energy access to get affordable access to loans and money in order to build them out. That's one of the biggest things. I've done some work in underdeveloped countries looking at renewable energy systems, and that kept, I was always working on the technical stuff, but it kept coming up again and again that it was about access to, what the fancy word we use is capital, but access to the actual money to get it done at loan rates that make sense.
Thank you. Are there any energy sources that you have focused on as an environmentally friendly option?
My favorite, the one I've worked with the most and is kind of my favorite, is solar energy, because we're already using it. Like if you ate today, that was solar energy, you know, a little bit up the road. So I've worked with solar panel systems. I've studied solar panel systems. However, solar's still complicated. If we put lots and lots of solar in the desert, we can disturb desert ecosystems. So one of the things that we are interested in is where are the places we can put solar where we've already made buildings and stuff, and maybe can we get enough energy from that instead of taking new ecosystems and putting solar in them. So I'm interested in all those things. I think most people would agree that you wouldn't want to cut down a bunch of trees and put up solar panels. But at the same time, the desert is also an ecosystem. So we disturb those if we put in lots and lots of solar panels. But solar's my favorite.
Great. I think you answered part of Carrie's question about the negative effects of solar power, but she's also wondering, does the environmental damage that the production of solar panels causes, do you think that is worth it?
So the evidence says yes. We have a couple of metrics for that. The way we measure it, we can measure the amount of energy it takes to make a solar panel, and then we compare that to the amount of energy we get from the solar panel over its lifetime. I don't know this number perfectly, but I think that number is greater than 10. It might be 20. So we get something like 10 to 20 times the amount of energy from a solar panel that it took to create it. Now the atmosphere doesn't care that much about the energy, it cares about the carbon. So we can do a similar metric. We can say, okay, well, how much carbon did it take to make that solar panel? And then how much carbon will it avoid by using that solar panel over its lifetime? And again, I don't know the number off the top of my head, but solar is a pretty clear winner in terms of the amount of carbon it takes to make it and the amount of carbon it saves over its lifetime.
Jake is wondering, what equipment was used to measure the temperature of the water in your demo?
So a couple answers to that. There is what we call a thermocouple, which is if you take, there's some magic science that if you take two dissimilar metals and put them together and then have one side heated up and then the other side of those two wires cool down, you get a little bit of voltage from that temperature difference. So inside the little probe that I stuck in the water are two wires with two dissimilar metals, and it's called a thermocouple. And then the circuit boards I showed you earlier were some circuit boards I put together that take that tiny voltage that gets created and turn it into a digital signal that we could put in a graph on the screen.
So Carrie is wondering about the role of methane.
All right, Carrie's got a great question. Methane is also a large concern. Methane is probably our second biggest concern after carbon in terms of greenhouse gases. And methane is an interesting gas because it is, I think the number is something like 100 times more potent at trapping heat than carbon dioxide, but it doesn't last in the atmosphere as long. And methane comes from landfills, it comes from cow burps, but it also spills out when we capture natural gas. So methane we often burn in our home, but we always spill a little bit of everything we get from the earth. So we spill some methane, and that is that is one way that methane gets into the atmosphere. So there are people thinking a lot about methane. It's very important. But because carbon dioxide is such a big problem, we often don't hear a lot about methane, but it's still worth thinking about. And there are a lot of agricultural practices that can impact methane emissions.
Rosalie is wondering what inspired you to care about the social justice aspects of science?
That's a good question. When did I really... I mean, I've always been interested in issues of social justice. When I grew up, I got a lot of racial slurs directed at me from kids my own age. So I've kind of always been aware of the fact that people see each other differently based on what they look like. So that's just always been something that that's been a part of me. And then so because I have that lens, as I went through my career, I saw the connections. When I was in grad school, I saw the connections between the way that the guys in engineering were treated relative to the way that the women were treated in engineering. And then I saw the ways that the data said that certain people were going to be impacted more. And I just kind of learned to see and hear those things because often those stories are invisible to us, and we have to learn to listen for them, and we have to learn to see them. So the more I learned to see and hear them, the more that I saw and heard them, and the more that I just realized that not only were they important, but they were actually just as important as every other concern. So I talk a lot about carbon dioxide, but when we reduce carbon dioxide, we're going to reduce asthma next to the highways, which often is a social justice concern. If we think about our agricultural system, we might reduce the pollution and problems with farm workers and communities related to our agriculture system. So all of these things are really deeply intertwined. But I think the most important thing would be to just, for many of us, issues of social justice are invisible to us because we don't see the bad side. As a male, there's lots of stuff that I don't see because I'm male and I get a lot of benefits from being male. Just kind of learn to see and hear them. And when people say stuff, give them the benefit of the doubt and listen to their stories. That can open you up to a lot of other challenging problems. So I'm part scientist, part engineer, and I love problems. And these are just more problems that I think are interesting to try to solve and make people's lives better.
Aaliyah is wondering, how long do you think it will take to reach 100% energy efficient world? Or is that even possible?
So let's see. So I think, let me reframe your question just a little bit, Aaliyah. I would say we want to reach a zero carbon world, which is really close to your idea. So I would just give you that little tweak. I think it still captures what you're thinking about. There are people that believe we could have a zero carbon world. So why do we think that? There are people who are designing homes where even in the winter, they are only heated by the sun and the people inside them. So you and I are all releasing about 100 watts of heat right now. There are people that are designing homes so that just from the energy from the sun and from the energy of the occupants, the houses stay warm. So California wants to start making what we call zero net energy buildings. So there's lots of things that we think we can do at very, very low carbon. And again, I think most of the challenges are how do we make it socially acceptable and how do we make it economically acceptable?
I think we have time for one more question. How can you make appliances more efficient?
Well, it depends on the appliance, and often let me give you sorry, I'm thinking on my feet here. I think the best answer would be to reframe the question and ask if there's a different way. So a water heater, most of us use water heaters that are natural gas, and they're very efficient. They convert probably 90% of the chemical energy from the gas into the internal energy of the water. So they can't get much more efficient, but they'll still be, even if you make them more efficient, they'll still be releasing carbon dioxide. So some people have thought, well, wait a minute, what if we use something called a heat pump to heat the water? Or what if we run a bunch of black pipes on the roof and heat up the water with solar energy? And so then they said, okay, so to use the language we used earlier, they said, well, wait a minute, are there different kinds of energy conversions that we could use that will give us the same thing we want, hot water, but for less carbon dioxide? And if you look at a solar system or a heat pump system, those can actually can be much more efficient in terms of the amount of carbon they release for every gallon of toasty hot water that they release. So often rethinking about, am I using the right energy conversion, can be a way to get much more carbon for the things that we want.
Great. Well, that concludes our question and answer period. Is there anything you'd like to say about the handout for today?
So we are going to start, the handout is going to start with just asking you to identify some energy and then energy converting devices in your homes, kind of do a little scavenger hunt, and then talk about what kinds of energy conversions you think we're doing. And then for those of you that have access to a stove and some measuring cups, we are going to heat up some water, much like I did. The one thing that I realize now that I neglected to say is that we don't know, when I was heating up the water, it was invisible to you. Hot water looks the same as cold water, unless it's frozen or unless it's boiling. So the main thing is that when water boils, it is very close to 100 degrees Celsius. No matter where you are on the planet, no matter what, at room temperature, excuse me, at our normal air pressure, boiling water is 100 degrees C. So that's one fact that ends up, so you're going to put water on the stove. 4 cups ends up being about a kilogram of water. You'll do the math and you will see by multiplying a couple of numbers together what the power on your stove is. And so we're going to have people in the breakout rooms to help you with that and answer any questions. Anything else I should mention from that, Milo?
I don't think so. I think we're ready to create the breakout groups.